And I know that the some of our students got infected by COVID. So if you are not feeling well joining the course, you can later on just watch the recording, uh, and hopefully you can very soon can feel better. Okay, I think we can start our course. So change this to my notes. Okay, let me go to new slides here. Okay, wait a moment. Okay, sorry. Okay, I think we can start our course. So for today's lecture, I would like to focus on a new chapter, this chapter 8. So chapter 8, let me write first chapter 8. Um, so your textbook, if you have the textbook, we have up until chapters, I think 11 or 12, I forget. But we are just focusing from 7, 8, and 9. That's for the whole, for the rest of the week. So we will still have chapter 8 and chapter 9. And hopefully chapter 8, I'm trying to finish it by maybe 3 meetings or maybe 2 meetings. So today's and next Monday, or even a little bit on Thursday, and then continuing directly to chapter 9. Or maybe in between we have some exercise like the one that we did previously on Monday. So so chapter 8, we will deal with the balancing on non-reactive non-reactive process. Okay, so just recall that on open system, we can say that the kinetics, potentials, and the work shaft all is negligible, because in open system we are looking at when the mass transport, okay, across the boundary. It means that we are looking on a bigger picture. Since kinetics, potential, and work shaft, their energy in, we can say that it's restricted on the small area, on the process, on the system. Then we could say that their energy is really insignificant, rather than if you compare with the heat flow or the enthalpy at the overall system. So in the open system, we can say that they are negligible. So uh, we could write, so in as implications, so implies that our heat flow is just the change of our enthalpy. Okay, I hope this is very clear for open system. And now we could have the delta. We could say that since it's open system, then the mass will have some impact. Okay, and it will gives the enthalpy some significance. So this is the output, and this is the input. Okay. And we know that this enthalpy, we call it specific enthalpy, right? This is just a little bit review on an open system that we did in chapter 7. This is specific enthalpy for the inlet system and outlet system. For the stream components, at their they have, this is important, the key is for the specific enthalpy. Why it's called specific? Because they are having specific processes, right? Specific process. or specific process conditions. Maybe that will be very clear. Specific process conditions, which are usually described as, maybe let me write in red, described in temperature, pressure, phase, or maybe state of aggregations, state or of state, state of aggregation. And they have comparable situation with their reference. Where we say that we need to have the reference for all this enthalpy, because remember that the enthalpy is a state property. We need to know the initial start and the end points of the our measurements for the enthalpy. And we are usually, okay, to know how much the measurement for the specific enthalpy, we sometimes we check the tables, right? Check tables for some specific enthalpy, okay? For some temperature and pressures, right? Like you have the saturated steam, you have superheated steam, etc. You know that the value of the enthalpy from the table. Okay, hope that's very clear. So this is actually the last section of our discussion. So we are having this this conclusion. Okay, now what happened in chapter 8 is, so this is all in chapter 7. So in chapter 8, what we deal is we need to evaluate our delta or the internal energy, where the table for the specific enthalpy and specific internal energy are not available. So this is the problem in chapter 8 actually. So you can get some story behind. This is the story behind. So we need to evaluate the delta for enthalpy and internal energy, where we are not having any tables for their specific enthalpy or specific internal energy. Okay. So we are going to have some approach for this measurement. Okay. Now from here, before we start to look on more about the equation itself, how do we balance our equations for this case, to evaluate the delta for the enthalpy or internal energy, what we would like to do is to give you more introductions on the reference, okay, the reference states. We may heard like from the previous sections about the reference state, but let me just make sure that we are on the same page for the reference state. Okay, first, the idea that we need to keep in mind is, first, the absolute value of the specific internal energy and specific of the enthalpy. The enthalpy, we never know. We may never know. We never know the absolute value. But to use or to measure or to determine the specific enthalpy and internal energy, we may not need absolute values and the specific enthalpy at specified states. What we are going to do is we need to know the delta U and the delta H for specified change of state. Let me make a little bit smaller for this one. Okay. So what we are going to do is we need to approach the delta for some change in the state. Okay. So we need to determine what state it is, right? How to determine the state. Okay, let me put into a new page. So if you want to take notes from here, we can take notes this one. I think this is important for chapter 7. Some ideas that you need to conclude from chapter 7. Okay. In chapter 8, this is the whole idea. So we need to evaluate this when we don't have any tables that is not available for some calculation. Okay, let me go through the next page. Okay. So choosing reference state for a species and determine the delta internal energy, specific internal energy is the delta internal energy is equal to specific internal energy that we are going um, to to take its value minus its reference. So this is important to take the reference data. And if we set that the specific internal energy for the reference equal to 0, then we know that the delta will be equal to the one that we are going to find. So we say that this is specific internal energy at that state relative to reference state. Okay. Okay, wait a moment. What? Okay, now from this internal energy, then we can also include the enthalpy. Okay, we can include the enthalpy from the H Okay, so we can include our enthalpy from here, from this definition. So this is a specific volume of the species at given temperature and pressure, temperature and pressure. And that is how the table can be drawn or can be created from this assumption. I mean this assumption here, the reference state. Okay, if you look on the table B7, table B7, for water vapor at 400 degrees Celsius and 10 bar, we will get specific internal energy is 2958 kilojoule per kilogram. If you look on B7, according to your appendix in the textbook. Okay. The reality is this amount of value is not the absolute value of the specific internal energy. This amount of value is our approach relative to the reference state. So this means that the specific internal energy of water vapor at 400 degrees Celsius and 10 bar pressure is 2958 kilojoule per kilogram relative to water at the reference state. Okay. And then from here, from these numbers, we can also get the enthalpy, which is the internal energy plus pressure and volume, specific volume. Now, as in calculations, we might have pressure is 10 bar, so 10 bar some conversion, okay, some conversion, and then some value for the gas constant. Gas constant is kilojoule per mole Kelvin, defined by conversions is 4 bar, liter per mole Kelvin. Yeah, you need to check the unit conversion. Okay. Now we get the enthalpy from here is 3264 kilojoule per kilogram. Okay. Okay, I guess that's the idea of reference state. So whenever you look on your tables, it's not the absolute value. Okay, it's not the absolute value of those specific for specific enthalpy, internal energy. They are all using a reference. And usually, using reference means that they take the reference usually 0, like when the reference is 0. Okay. Okay, now from here, since we are dealing with reference, and reference means that we need to evaluate somehow. Wait for a moment. Let me check. Is my voice still can be here or no? My voice still okay, or there's slight clear? Okay, wait. I need to. Okay, thank you, Chantong and Rivaldo. Let me check my connection. Okay, I think it's clear. I don't know why. Okay, I think it's clear, right? Okay, now since we're dealing with this reference state, okay, let me go through the idea of, or maybe I will write that since this internal energy and the enthalpy, this is we call their state properties. What state property means? Means that the values depends only uh, on the state of the species. Usually states on temperature, pressure, or the phase. Okay, the phase. Solid, liquid, and gas. So what does it mean? They depends on the state of the species. It means that uh, it doesn't care how you get the value. For example, or let me write another note that it doesn't depend on how the species reach the state. So the process in between, you don't really need to care about that. What you care is you have some initial conditions and you have the state that specifically say about that species in that state, and that's it. That's the one you need to be aware of. Okay, and we call this to know or to imagine or to visualize. Okay, to visualize, we call this. We need to take this into our hypothetical process path. For example, you may have some some steps or some path. Okay, so from state A, you go to B, you go to C, and then end up with E. And you can also take another route. You go to E and then directly to D. So whichever you take, so from A, D, should be have the same conclusion, has the same result. Depends on your observation, which one you are dealing with, and which one you are going to take some observations. Okay. Okay. Now, this chapter, so chapter 8 and chapter 9, so let me write here. So chapter 8 and chapter 9. So you will learn how to, or maybe let me write, learning how to calculate internal energy and enthalpy, the change in enthalpy associated with first is the conditions. There will be change in pressure. T is constant. Phase also constant. And then second, there will be change in T. So the state means temperature, pressure, and the phase or aggregations. So change in temperature, pressure is constant, and phase also constant. And then the other one is change in phase. Change in phase. T is constant, and P also constant. Okay, so the phase can be changed, like the vaporizing, condensation, sublimation, something like that. Okay. Fourth, mixing two liquids or dissolving a gas or solid in liquid at constant T and P. So pressure and temperature are constant. And the fifth one, this will be chemical reaction at constant temperature and pressure. This will be chapter 9. And the rest will be, this will be chapter 8. Okay, so I think the first three changes is pretty much you can know intuitively from three variables that we have. We have temperature, we have pressure, we have phase. So each one you may have changes, and the other two will be constant. Then those three changes in variable will be our discussion in chapter 8. At least from 8.2 to 8.4, we will discuss more about that. Okay. So basically, since we are not having any tables to look at in chapter 8, what we can do is creating this hypothetical process path at the beginning. So visualizing the path you are taken to observe the process is the very first steps, okay, for the chapter 8. Okay, so let me give you a context here. let me give you some words to take on. So since the specific enthalpy is state property, the delta of the specific enthalpy calculated for hypothetical process path, hypothetical process path which constructed for convenience. So this is that we need to apply. Is the same as delta H for the path actually followed by process. Okay, for example, solid phenol or this phenol, and then it is solid. T is 25 degrees Celsius. The pressure is 1 atmosphere. It's converted to phenol as in paper. T is 300 degrees Celsius and the pressure is 3 atmosphere. Well, if we had a table, okay, if we had a table for phenol, then the delta H, we can simply say that this is the subtractions for the outlet, the vapor. T is 300 degrees Celsius, P is 3 atmosphere, and then minus the inlet, which is the solid, with T is 25 degrees Celsius and pressure is 1 atmosphere. But we don't know, right? We don't really know how we get this in numbers. Since we don't really know, because we don't have the table for phenol, what we can do is we can construct a path. Okay, we need to construct a path. Okay. Okay, let me just put my drawings from the textbook, here. So phenol, okay, this is the conditions. So this is the starting point. Okay, and this will be the terminal point or the end point, right? So what we are going to do is we are going to approach some other delta that might have been calculated. Okay. For example, we may take this 25 degrees Celsius goes to 42.5 because in this 42.5, this is the normal melting point of phenol. And you may look on the table B1. So table B1. So in chapter 8, most of the time, you will be dealing with table B1 to look on either the melting point, okay, or boiling point, okay. So if you check the B1, that will be your cases. And why do you need those normal and melting point? To construct some process path, okay. So I hope you get the idea. Okay? So before in chapter 7, Mostly you are likely to use table B5, 6, 7, which related to vapor, water vapor, for saturated steam and superheated steam, right? But for now, since we are dealing with other species, like for example phenol, like this one, then we need to have another states. Okay, so the states that we are talking about is when it has the some changes. Okay, some changes. Okay, for example, change in phase or change in the normal melting point, like this one. Okay, and of course, if you have the melting, then you will need to change the phase. We take it into different age. Okay, so the first one is when its temperature change. The second one is when the phase also change. Remember, you need to construct this path separately. Okay, temperature and phase you need to construct separately. Becomes two different delta H. Okay, remember that in here we consider this becomes two different way, or three different way here. Change in pressure, in temperature, and in phase. Okay. Okay. Next is we have another change in temperature. So another temperature change. And what is this temperature about? This will be the boiling point. Boiling point of phenol. The normal boiling point. Okay. And then we take another delta H, which change the phase. Okay, phase change. Right? And then from here, we still have increasing in temperature, because this is the temperature that we are going to evaluate it at the end. Okay, so there's no change in temperature anymore. So 300 will be the last changes, right? But we still have the atmosphere change, so the pressure. So the last one will be the pressure change. And thus we have our delta H. So delta H we can simply construct with this delta H1 plus delta H2 plus delta H3 plus delta H4, 5, and 6. Okay. Now H delta we need to evaluate. Okay. So later what you can do is evaluate H delta H. And what we are going to discuss more is we are going to look on how to evaluate each of this delta H. But that will be later cases for next section. Okay. I will go for some general procedure first, okay? And then we are going to have much more discussion on how we are going to evaluate each delta H here. Some of the delta H we can compute using table B1. Okay, some parts of it we can read the table for the phase change. Okay, we can read the table. So for delta H2, delta H4, we can read the table B1. And for other case, for the data age, we need to have some evaluation through some, I believe, some integrations that we need to take. Okay, let me move to the next page. I hope you guys at least get to know the idea for hypothetical process map. I believe it should be similar to what you did in chemistry, in basic chemistry, right? You learn on this path. Okay, let me move to the next page. Okay, let me write uh, energy balance procedure in chapter 8. First is, of course, material balance calculations. Okay, it means that you need to know the mass and or the mass flow, okay, for each streams, and then you need to make some um, equality between the input and output as usual. So secondly, write the energy balance open or closed system, and then delete any negligible terms. And three, choose a reference state. This is the state that you can choose is can be based on the phase, temperature, and pressure for each species involved. For each species involved. Okay, for a closed constant volume system, so it's a closed system, and the system has a constant volume. Construct a table for initial and final amounts of species. It can be in mass or in moles. That should be a table. And specific internal energy relative to the chosen reference date. This is the first one. For open system, construct a table with columns for inlet and outlet streams for inlet and outlet stream components, flow rate. So it can be mass or mole. Okay. Okay, and specific enthalpy relative to the chosen reference states. So both are constructing a table. Okay. So after we construct a table, then we calculated the required values. So calculate required values for the specific of internal energy or the enthalpy. And insert values. And to calculate the values, we need to choose the reference states wisely. Sometimes we choose reference state that easily to be counted, like in zero or other states as well, that we are able to give significance results. And then we calculate with all the values already been input, then we calculate the total system. So for the closed system, the delta U sorry, should be finally minus initial. Or using the mass and in open system, or okay. And second, calculate any work, kinetic energy, potential energy, okay, that maybe you haven't dropped from the energy balance. If you have this, still you have this terms you need to calculate. And 8, solve energy balance. So input all the terms to energy balance. So we may have, for the closed system, and for open system, okay. Okay, this is more or less the procedure that we might need to follow. So basically, what we can look here is, firstly, we need to evaluate the calculation for the mass balance, the material balance. The secondly, we need to write the energy balance, either it's open and closed. This is actually the equation that we might need to write, but actually you can skip for a while for number two. We can focus first on finding the enthalpy or the internal energy. That should be more approachable. And then we find the reference state, and then we input our numbers, okay, our values, and then we can calculate the delta for internal energy and enthalpy. And after that, we can take calculation for other terms as well, and then we can solve the energy balance. And then we might have some answers, like maybe we need to calculate the heat flow, or we need to find the the delta of internal energy that we need, or enthalpy. Okay, we need to solve the energy balance. I think I can give you a more practical approach on how we can generate this procedure in a practical example. Okay. Okay. So basically, this is a general procedure. Okay. So if in between we might need to construct a process path, that will be a different story. So this will be probably will affect this internal energy or enthalpy. Okay. So let me start with giving you some basic some practical approach. So if we have this acetone, it's partially condensed out of a gas stream containing 66.9 mole percent. Okay. So we have 66.9 mole percent. And it's vapor and the balanced nitrogen. So nitrogen will be balanced with the acetone. So you have the nitrogen will be 100 minus 66.9, right? As you might see that this is our nitrogen here. This is the acetone. This is steady state. I forgot to mention. The process is steady state. And what we need to do is we need to calculate the cooling rate. Okay. Okay. The chart is already been given. Okay. So we have a condenser here in the middle. So partially condensed. Partially condensed means that we would have two streamlines for the acetone. Okay. And the other part still have the balance with the nitrogen, and they are in the same states. Okay. So first, perform material balance, but since we already have in terms of mole, they already given, so no need to calculate. So maybe we need to write the energy balance. So energy balance steady state open will be Q and there's no mentioning about the work shaft, so we would have it, this is to be 0 for work shaft. And what else? I think potentials. There's not mentioning any potentials. I think there are no change in temperature, or the temperature change is small. I think we can say also the kinetics is 0 for this one. So we can reduce the balance to be heat flow equal delta H, or this is equal to the summations okay. So we can focus more on this the delta for the enthalpy. And now we can choose the reference state. So the reference state states for acetone and nitrogen. So according to what we have in the states here, I think for the acetone, it is better to choose this 20 and 5 atmosphere, 20 Celsius and 5 atmosphere. So for acetone, we choose for 20 degrees Celsius, 5 atmosphere, and liquid. That's the state that we are going to take it as a reference. And the nitrogen will be 25 degrees Celsius, 1 atmosphere, and it's gas, because I think that's the most plausible conditions for the nitrogen. You can make sure this from table B8. This is specific enthalpies of nitrogen at this gases phases. Okay, and then we construct a table. So table inlet outlet enthalpy. So substance, and then all the species, the mole, the specific enthalpy, and also mole out and specific enthalpy out. Okay. Okay, substance, we can write substance as acetone. We have two acetones. First one is liquid, the second one is a vapor. So acetone vapor. So we take this 66.9 and let me write this as H1. So 66.9 from the first one here. That's the vapor, the input. And I think we need to make another line, sorry. Here. And then out is 3.35 H3, and then the acetone for liquid. The input, they don't have any liquids, right? So we can just take it 0. And output, we have 63, okay, mole. 63.55. And since this is the one that we are going to use as a reference state, okay, we choose reference state for the acetone at this, right? So at this moment, we will have the enthalpy as 0, okay, because it's there, our reference state. And the nitrogen, we have 33.1, that's from the picture given, 33.1 here. And the enthalpy, let me write H2, and out still have the same, and still writing same also. So we have 4 specific enthalpy. Okay, now the next step is we are going to find the numbers for this 4 enthalpies. Okay. All the numbers we can determine from the flow chart given, okay, at the beginning. So now to determine each part for the enthalpy, we might need to use the to construct the process path. And for details process path, we will elaborate later on in the next section. But let me just write the H1. This is specific enthalpy. Let me explain this. Of acetone, vapor, it's 65 degrees Celsius and it's 1 atmosphere relative to acetone, since our reference state is the liquid, 20 degrees Celsius, 5 atmosphere. Yeah, another thing that why we need to choose this as our reference is because we are having this, if you look on our chart, they have 20 degrees Celsius and 5 atmosphere at these 2 species here, which means if we take this state as our reference state, it will help us to make our calculations easier. Okay, so this will be equal to the delta H for acetone, liquid, 20 degrees Celsius, 5 atmosphere. This is acetone, vapor, 65 degrees Celsius, and 1 atmosphere. So we will have a process path for this, process path. And we are going to see that what is going to happen is we choose this as our initial, and this is the end point for our construction path. Okay, so we have change in the phase, change in the phase, change in the temperature, and change in the pressure. Okay. Now, of course, we need to have some idea on how this liquid can be vaporized. Okay, so at what temperature, that will be the idea. So we might have another delta for maybe 3 or 4 deltas here to get into our calculation. Okay. Okay. All right. Let me give you the basic idea on what will be in our calculations in the next section. Okay. Let me write first. Okay. So we still in this this discussion for finding the enthalpies. So in 8.2, we will have this formula. So we will have the pressure change for constant volume, and the value for acetone liquid can be determined as 0.0734 liter per mole. This is taken from specific gravity specific gravity 0.791 in table B1. So your calculation a little bit, you will have some exhaustion. Okay, you will be a little bit tired doing this, but this is how we approach. Okay, hopefully at least you need to get the idea first. Okay, you need to get the idea first, and then 8.3, you will get the delta H will be equal to the integrations from T1 to T2 for some Cp dt. This is the capacity, the heat capacity for a constant pressure. So this is constant pressure. So this formula is a formula for heat capacity at P constant. And you might need to see this in table B2. So I will give you the general procedure and then the idea on getting at least getting this table first, and how to get a specific enthalpy. We will deal more in the later sections, which includes the 8.2, 8.3. Okay, and just as introduction here, I will just write for acetone. So for acetone, liquid or vapor, we might need to write the acetone as in table B2. Okay, acetone liquid. This will be Cp equal 0.123 plus 18.6 T. Okay, this is the formula, and then you need to put this formula inside the equation here. So put the formula for Cp, and then you need to use integral. Okay, I hope that's very good. So I believe your calculators can do this for you, right? You just need to type in the formulations, type the temperature that changed. Okay, and then you have also, aside from the liquid, you have the vapor one. We have Cp equal to 0.07196 plus 20.1, and still we have it's a little bit long, so let me write a little bit left here. And then we make it a little bit smaller. So minus t squared. Okay, so you have t squared and then plus 34.76 negative 12 t cubed. Okay, so a lot of calculation here, but supposedly to it could be calculated easily through your calculators for all the integrations. Okay. Okay, and then the 8.5, 8.4, sorry, 8.4, we deal with the heat of vaporization. Okay, or we call this delta enthalpy, and then we have some V vaporization there. uh, usually this delta will correlates with the boiling point. So boiling point for vaporization. BP means boiling point. So this is um, from liquid phase to vapor at normal boiling point. And you will need to look on the table B1. So table B1, this consists, if you look on acetone, the boiling point will be 56 degrees Celsius. And the delta for the heat vaporizations is 30.2 kilojoules per mole. Okay, after we get this, all the delta, okay, so we can construct the hypothetical process path. Okay, so what we need to write is, let me write the starting point is acetone, liquid, 20 degrees Celsius, 5 atmosphere. So I will write this as our starting point, just to look at. So I will start from this liquid, okay, and then to get into our vapor. So this is liquid, vapor, right? So let me write in terms of liquid, okay, first liquid, and then we are going to get into our vapor. This is our delta H, right? Our delta H. But then we have some change. First is changing in terms of pressure, for example. First is pressure. Let me change to liquid, 20 degrees Celsius and 1 atmosphere. We change in pressure. We might write this as, since this is actually we are going to find out the H1, so all will be having H1. So this will be the delta H1A. And then the next part will be getting increase in, so it's still acetone, liquid, and then 56 degrees Celsius and 1 atmosphere. Let me write this as delta H1B, and then getting increase again. This is the phase change, so we have the vapor. So this will be delta H1C. And then we have the final, right? This will be delta H1D. So we need to calculate all these three A, B, C, D informations for our total enthalpy. Okay, this is delta H, H1. So we can say that delta H1, or we say the H1, as we are going to focus more on this H1 here. We could say that H1 is delta H1A plus delta H1B plus delta H1C plus delta H1D. Okay. Okay, for the first one here, let me write each of the components for the formulations besides this formula. So this is equal to volume, constant specific volume of the acetone for liquid, and then multiply with 1 minus 5 atmosphere. And then the B will be equal to integration from 20 degrees Celsius until 56 degrees Celsius of Cp for acetone liquid dt. Okay, and this is also to write completely plus the heat of vaporization, so delta heat of vaporization of AC. Okay. Oh, sorry. This one should be change phase change. Sorry. What I'm including here should be here. So this is a heat of vaporization. Heat of vaporizations that you can compute from the table B1. Table B1. And the D will be another Cp dt from 56 to 65. This is Cp for acetone in vapor dt. Okay, now you need to calculate each one. Okay. So we need to check the specific volume for acetone, and then we need to check the Cp formula. Like I mentioned, I think I mentioned here, you need to input this formula using the integrations from this 20 to 56 and the other one from 56 to 65, and check the table B1 for the heat of vaporizations, and then we get the number for the H1. Okay, the H1. So H1 we get from the calculations. If you calculate all, then you will have this 35.7 kilojoule per mole. This is also from table B1. Table B1 and use the specific gravity. Well, it's a little bit messy and complicated since. And then for H2, H3, and H4, you can proceed with similar manners with H1, and of course you will get some numbers from these calculations, okay, from the proposed path. Okay, now from there we could have oh yeah, actually this is the table that we did before. So we need to check the, so H1 is 35.7, and doing the same way with what we have in H1, we would get this is 1.16, 32, and negative 0.1. After we get all the numbers, then the idea next is to check the delta H, the total delta H. Okay. Now from all the numbers, I think it's easy to be imagined. So the output and input. So we could multiply N and H. So we'd have output as 33.35, 32 plus this will be 0, so we will have a 0. So plus the 33.1 and negative 0.1, and then minus the 35.7, 66.9 and plus 33.1 and 1.16. Type in your calculator, we will get this 2,320 kilojoule per second. This is the delta H. Okay, and then we solve for energy balance. Since there is no other terms, we could write the energy balance as the heat flow equal the delta of the heat, the enthalpy. This is negative 2,320 kilojoule per second, or we could convert directly to negative kilowatt. So this means that the cooling rate, so heat must be transferred from condenser at rate of 2,220 kilowatt. Okay, so from condenser need to be released outside this much for to achieve the required cooling and condensation. Okay. Okay, so I think this part, okay, the hypothetical part is the essential part in chapter 8. So I need you to focus on how to get uh, the idea on to construct the hypothetical process path. So you'll be focused more on some table B1 for some specific gravity, the heat of vaporization, the boiling point of the melting point, table B2 for the heat capacity formula, okay, for some substance that will be basically what we are dealing with in chapter 8. Okay. Okay, let me just recap. Okay, what we did in a quick summary. Okay, in quick summary, what we did here. Okay, this is simply a little bit messy, but let me recap all the um, what we did in terms of calculations and um, our diagram, our flowcharts. Okay, so let me write in a more so recap on what we did. Let us consider what we are doing before in more different perspective. So the process that we might have is first we have the 66.9 mole of the acetone, right, for the vapor one, and we have 33.1 for the nitrogen, and we have the state at 65 degrees Celsius and 1 atmosphere. This is the beginning, the vapor that goes into the condenser. And then if we look on the change that we have, it goes to convert this vapor into liquid or acetone, and still it has a little bit of vapor for acetone, and still it goes through the nitrogen. It doesn't um, change anything in the nitrogen, and we have the second state, which is 20 and 5 atmosphere. So all this is actually what we are doing is we find the delta H in between of these two states, right? Okay. And to calculate this delta H, we construct, so to calculate delta H, construct a path, right? We construct a path that is start with a 66.9 mole acetone in vapor. Let me write all the things here. So this is the true delta H. Oh, let me just copy this. Okay. So this is the true delta H, and we construct some path that maybe let me write just the delta H A and delta H B to simplify what we did before. Okay, we construct the path with some reference. So the reference conditions, we take the reference conditions for the acetone is liquid and then 20 degrees Celsius and 1 atmosphere and 33.1 mole of nitrogen, 25 degrees Celsius and 1 atmosphere. That's our reference that we take. And then the delta HA, this is, or let me write in, maybe I will write here. So delta HA is the negative of delta H in the process in which that the acetone and nitrogen go from reference condition to the inlet conditions. Or we could say that the delta H A is the negative of the summation of the inlet. I think we can make it more clear. We go here and make it a little bit smaller. Okay. And similarly, delta HP. So delta HP is when acetone and nitrogen go from reference condition to the outlet. Or we have the delta HP is equal for summation outlet. So the overall equation will be okay. Now you know that why we have the negative here is to make it the negative here. So it is giving us a slight impressions that for the next section we are going to focus more on the process in this in between this path. So since we have different path in between this delta H. So let's say this delta H is our true path. Okay. The path that we may construct may have different way, right? So in the next sections, we would have to elaborate those paths, okay, that we might have to that we might need to calculate. Okay. So so actually I start with a general procedure that you can see of what we have here. Okay, so first we deal with the reference state, we deal with the here we deal with some specific enthalpies that we need to check and we need to find. And how do we find this specific enthalpy is precisely the one we are going to discuss in the next section. Okay. So we will discuss more on this part, also this part, the heat of vaporization. Okay, let me go through the next page. But before that, is there any questions? I know this is a little bit messy and complex, but I hope, okay, you get the essential parts for this one. Okay. The essentials is the process path. That's the important point, and the reference state and the process path. Okay. Okay. If you have any questions, you can try to.
Oh, sorry.
Yes.
No question.
Oh, okay. Okay. Um, Maybe I will add one more uh, section. So I believe I said that in this one we have the 8.2. So let me just give you some details on 8.2. This is very short, so I hope I can finish 8.2. So let me give you the idea. So 8.2 we have a change in pressure at constant temperature. Okay. So we see that, or we observe thing experimentally before. We showed that uh, the internal energy nearly independent, near that internal energy nearly independent of pressure for solids and liquids at temperature constant or constant temperature. Okay, and as in specific volume also. So therefore, as implications, if the pressure of solid or liquid changes at temperature constant, we can write that the change in internal energy is approaching zero in approximation, and the delta H thus we can write in terms of U plus P phi, right? P phi, and let me write P as delta P phi, okay, P phi, like that. And we could write that the delta H will be approximately equal to the volume and then delta P, specific volume and delta P. So both specific internal energy and the enthalpy, they are independent of pressure, independent of pressure. So generally, we could assume this is zero, and delta H can be also zero for some gases. for a gas in isothermal pressure change, unless it is below 0 degrees Celsius or above 1 atmosphere. And of course, if you are having tables so if you have this table, if if we have a table for U and enthalpy for some temperature and pressure, then this assumption is no use. No use for assumption. Okay, so the one part is important here is this delta H here. Okay. Okay, but mostly the gas in our problem set mostly are ideals. So I think no need to make such assumption. Okay, I think I can go for one more, okay, just to show you change in temperature. Okay, so this will be 8.2. Okay. So 8.3, this will be about the change in temperature. The important terms in this 8.3 is the sensible heat, so sensible heat and heat capacity. Okay, now first, to give you some illustration, sensible heat means that we could sense the heat. We could sense the heat. So it could be described as heat that transferred to raise or lower the temperature. Or, yes, I believe it should be very clear from the words sensible. Sensible means that it can be sensed. Okay, you can sense the heat, which means you can measure the heat, or you can measure the temperature. So it means that the heat that can be tracked through some measurements, you can say that it's sensible heat. Okay, and we know the heat from our two approach for the closed and open system. So this is closed, this is open, right? Open system, closed, open system. Okay. So we ignore the kinetics, potentials, and works to make this happen, um, because they are insignificant. Okay. So to determine the sensible heat for heating or cooling process, we need to be able to determine the delta U or the delta H for the specified temperature change. So we could observe some, or a graph here. Let me put the graph. We could observe from this graph for to describe the temperature and the internal energy. So we could say that this specific internal energy, or U, depends strongly on temperature. And if we raise or lowering the temperature, we could have this property showed in our graphs here. So if we take this, for example, from T1 and we add some delta T, we could have another delta U. And of course, if we have delta in any graph that we have, and if the delta is really small, we could have our definition with limit, right? If you remember calculus. So as the delta T approaching zero, you remember that like the calculus that we have, limit, we have this, right? Our limit definitions in calculus for the tangent or for the derivative. Okay, so as the delta t getting zero, the ratio this will be, we can say it can be our slope, okay, in terms of calculus. It is a slope of curve at t1, right? So we have from here, here, and here. Okay, that's the slope. And by definitions, this is our heat capacity at constant volume of the substance, or we could say that this is our Cp, or not Cp, constant volume means Cv. Okay, sorry, constant volume. So let me write here that Cv is equal limit delta t going to 0, delta u, delta t. Or we could say that it is with partial here, or we could say the derivative of u with respect to t. And we could have some small calculations in terms of mathematics from here. We could say that we can write the terms du is equal Cv dt. Okay, we could write here, and if we take the integration here, both sides, we could write that this becomes the delta u. This will be equal T1, T2, and we have Cv T dt. Okay, so how do we get the Cv? So Cv is actually the behavior, okay, the property itself of our curve. Okay. So from our curve, for some substance, they have some property like you have in previous problems that you have here. You have this. This is Cp. Okay. So you have some property that you get from the graph here. And it turns out that we might have this practically our approach to get our delta U. So we could say that this is not really exact, but we can say this is approximately equal. Okay, and it's if we take some for ideal gas, this will be exact solutions. For solid, or liquid. Good approximation. Not really that the same, but it's good approximation. And for non-ideal gas, this is valid if the volume is constant. Okay, we have now two different case for change in pressure, and this is change in temperature. Of course, for to get CP, it's on the constant pressure, but I will let the CP descriptions will be on the next lectures. Okay. Now I would like to give you some explanation again regarding our class, uh, our class, our online class, and especially for exams, because I think you already know that we have online classes until the end of the semester.
So would our exam also be online?
Yes, yes, online also for the exam. So let me explain what I'm thinking now for your um, quiz and final. So for your quizzes, it could be like I will make an online test like with the online platform. I believe you can do it from anywhere, anytime, as long as it's still in the durations. I'm planning to give you the quizzes next week for chapter 7. So quizzes chapter 7. So I will put the link. So I will put the link on Moodle, and you could click the link on the Moodle. Uh, like for example, you have some durations. So you have some duration. For example, durations may be 4 to 5 days. So you can choose from any days you are going to click. Okay, you click the link, and then it will go through some platform, and you need to complete the assignments. Okay, you can complete the assignments on the platform. Um, Basically, you need to answer each questions on the platform, and each question has time limits. I think some of you are already familiar with this. So this will range from the time limits will range from 30 seconds to 15 minutes, depends on the question. So I hope I will give you quizzes that the maximal time for each question, the maximal is 15 minutes. So if the times is like for example, it goes by and then you still don't answer it, I give you the options to not having time to answer, but you can answer after finish. But of course, that will be the grade will be different from if you answer it on the duration. Okay, so you could do this quiz, open notes. You can.
So like would there be an option where like we have no time to write answer? Because I feel like sometimes we do the calculations and there's a time delay just because we have to like use our keyboards or whatever to like input the answer, and sometimes like navigating through the keyboard is a bit like difficult, especially writing out units and so forth. So would there be an option of did not have time to write answer?
Yeah, yeah, yeah. I will add do not have time to write answer. But of course, the different it will be different in the points that you are going to receive at the end. Okay, so I will give you some clear guidelines later on. So I think hopefully next week. So we can say we could say that at least 2 or 3 meetings we still have chapter 8, and maybe after that on the weekends. So not this weekend, but maybe next weekend. So next weekend that I will provide you the links. So I need to prepare the questions first, and hopefully I can give it to you next week on the weekend. So that will be the quizzes. For the final exam, I'm planning to use the same platform, but we are going to take our exam on the same time. So I will supervise the session, and yeah, I need to recheck and maybe check all the possibilities that I can afford, and probably the exams will be also open notes. Okay, so I just give you open notes for the online exam. Okay, so that means that probably the questions will be more it's having more observations and having more probably more difficult than usual the usual exam. Okay, but I hope if it's open notes, then maybe it can also help you to just focus doing the exam by yourself. Okay, so I think that's it for today. If there's no questions, so I will just put
Okay.
yes.
Can I ask that when is the final? Like approximately time?
Yeah, approximately. Uh, I hope my target is before June before June 10th. Before June 10th.
Or before June 10?
Yeah,
Oh,
and that would be the limit for me. So we could
okay,
have
thank you.
we could have also early exam also. It depends our class. Okay? Depends on our class.
Okay, thank you for this.
Yeah, you're welcome. Okay, any other questions? If not, then I think we finish for today's class. Uh,
Okay, so thank you very much.
yeah, thank you for joining. Okay, thank you for joining. The idea, chapter 7, chapter 8, we deal mostly with tables. So I need you to, if you don't have the books, then you might need to copy the appendix, okay, as your reference. Okay. Okay, I think that's all, and see you later. Okay, so you can leave the meeting.